So, from today we are going to start a new topic, namely that of model checking. So, previously we have looked at simulation based verification, we have looked at equivalence checking algorithms. We saw when we studied simulation that assertions are becoming a very important component of the verification flow, and so assertions are broadly checked in two ways. One is over simulation runs and the other is over statically. So, you use static methods which are called formal methods to check whether a property holds on a particular design. The underlying method is called model checking. So, that is what we are going to study for a few lectures starting from today. So, the agenda is that we are going to have a quick overview, then we will have some discussions on properties, automata and state machines, and then we are going to dive into the actual model checking algorithms.
So, this model checking is part of formal verification?
Model checking is the formal method underlying formal verification. Okay. So, model checking is not just something about verification of circuits, it is a generic methodology where you have some specification and some implementation, and you are trying to figure out whether the implementation is a model of the specification. It is not equivalence checking, because for the same specification there can be many valid implementations. So, and those implementations may not be equivalent in the logical sense. If you compare their input output behavior, it may not be the same, okay, but both of them satisfy your specification. So, therefore, equivalence checking tries to make sure that there for the same sequence of inputs, both the machines produce the same sequence of outputs, right, then they are equivalent. But here we have a specification, and any implementation which models that specification is a valid implementation. Okay. So, the name model checking comes from that paradigm, that I have an implementation, if it is a model of the specification, then it is valid. So, checking whether it is a model of that specification is the model checking problem.
If you are doing the equivalence checking, then is there a need for model checking also?
Yes, because the specification here is at an abstract level. You can compare to state machines, yes, but here you have a specification corresponding to which you can have many implementations, right. So, it is a language containment problem as opposed to a language equivalence problem. Okay. So, what is formal property verification? So, it can be interpreted in two ways. One is that it is verification of formal properties, so formal property verification, or it can be interpreted as formal methods for property verification. Now, typically by formal property verification we refer to the second one, that is formal methods for property verification, but both of these items are very important requirements in the verification community. So, we will broadly use this classification, that when we say verification of formal properties over simulation, then we will refer to that as dynamic property verification, or DPV, and when we refer to static or formal methods for formal property verification, we shall refer to that as FPV, or formal property verification. This is the setup for a dynamic property verification flow. So, you have the design under test here, and you have the test bench here, and this is the interface between the two. We had seen that you can write properties and then bind them with this interface, right. We had seen how that is done in system Verilog previously. So, when the simulation takes place, then the assertion monitor, which are property checkers, keep tracking whether there is any property violation on the simulation. If there is a violation, it flags the error, right. So, this typically helps in debugging. Now, what the important thing that we must realize is that because this flow is there, because dynamic property verification is there, people write assertions anyway. So, you write an arbiter, you write a code of an arbiter and just spray it with some properties like two outputs should not be asserted at the same time. You just write those assertions, not because you just want to verify this at this moment of time, because this particular module is going to get integrated into lot of other designs, and when in that integrated environment all the assertions are live. So, when the integrated simulation is taking place, it can find out that which property in which module failed and help you in debugging the whole system. That is a very important requirement. So, for every module that you write, the RTL designer is encouraged to write properties which are properties of the module and assume properties which are assumptions about the environment of the module, right. So, in the integrated environment, when the property fails, it could be because the assumption was not met. So, some invalid input scenario was driven under which the property failed, or it could be that the assumption was met, but the property failed, and that can happen because we did not formally verify the property. So, that particular input under which it failed never appeared in simulation previously, right. So, for all these reasons, the assertions are considered to be very important and they are spread all across the design, and today any chip design company, digital chip design company, use assertions to plug them in everywhere in the design. Now, the formal property verification flow is like this, that we have the device under test, and from that we extract out a finite state machine model, right, and we have the formal properties. The model checker, the tool which checks the properties, takes this finite state machine model as the input and the properties as the input, and then checks whether this property is going to hold on this model on the implementation for in all possible ways, right, or if not, then there is some combination of inputs and outputs under which the property is not met in the finite state machine model. So, that counter example trace will be produced by the model checker, right, and if the counter example trace is not found, then it says yes. Now, see that this is like satisfiability. If you have a satisfiable instance, then that witness is given and you can verify easily that that is a satisfying witness. So, given a counter example trace, you can easily see that the design has a bug. But if the model checker says that no, I could not find any counter example traces, then there is no way that you can double check that, because you see it is saying that I have explored all possible runs of the machine, of the state machine, and yet I did not find a bug. How will you verify that it has actually explored everything? You just have to take its word for it, okay. So, this is something that we have to live with, that whenever we go for a formal property checking algorithm, if it comes up with a counter example, well and fine. If it does not come up with a counter example, then we have to believe the tool, and there are approximate tools which will not be able to explore the entire state space, right. So, then if it says that I did not find a counter example scenario, it just means that it did not find it, does not mean that there is not a counter example scenario. So, we will have to see that how we build confidence using this kind of a algorithm, okay. It is very important, which is why we will look at things like coverage and other issues. So, the formal method behind formal property verification is called model checking. The algorithm has two inputs, a finite state transition system representing the implementation and a formal property representing the specification. The algorithm checks whether the FSM models the property. This is an exhaustive search of the FSM to see whether it has any path or state that refutes the property. Okay, so before we go further, let us understand which is the difficult part here. Right? The difficult part here you see is that the model checking algorithm requires this as one of the inputs. Okay. Now, for a typical large digital design, the size of the finite state transition system is huge. Right. Now, the algorithm is linear. The algorithm for all the model checking algorithms that we shall see, they are all linear in the size of this FSM. And whatever exponential there is, for example, LTL algorithms will have an exponential. The exponential is in the length of the formal property. Right. Now, see, the length of the formal property is typically not very large, because it's just one property that you are writing. How big will it be? Right. So, even if you have an exponential on that, or even a double exponential on that, then that does not hurt you too much. What hurts you is the size of this FSM. Okay. And remember, the size of this FSM is exponential in the size of the circuit. Right. So, if you have a k bit register, the size of the state space is 2 to the power k. Alright. This is where it hurts us, not in the algorithm. The algorithm is very good. It is only exponential in this and linear in this. So, that is not bad. Linear is, I mean, if you have to explore everything, I mean, linear is the best that you can get, because you have to visit all the states, all the edges, right. So, linear is the best that you can get anyway. So, that way that is good. The problem is how that we need to traverse this, and that is where it hurts. And so, people are finding out efficient ways of representing the state machine and traversing the state machine. That is where the whole fight is going on. Okay. To give you a quick history on the advent of formal property verification. So, temporal logics was I mean the logics that you see today, LTL and all, were brought into effect by Amin Newelly, and for which he received the Turing Award. So, this was about 2 decades ago, and then when model checking came into existence, in the sense that people started using model checking in formal verification, in very quick time the logics were adopted by Accelera, and the languages like system Verilog assertions and PSL came into existence, and they are now IEEE standards. And this integration into the existing industrial practice happened very quickly, and along with that the simulation tools started supporting assertions also in very quick time. Okay. In the formal space, tools started coming in. So, the earlier tools were SMV and VIS. SMV is the CMU model checking tool, and VIS is the Berkeley model checking tool. And now you have a new SMV, which is a more enhanced version of that. In the industry, you have Magellan, which is the product from Synopsys, and IFV or incisive formal verifier from Cadence. There are a lot of other tools that are there in the market today in the formal space. And this year, Clark and Emerson received the Turing Award for their contributions to model checking. Okay. Now, let us see how do we go about doing LTL model checking. So, we will first study LTL model checking, and then we will see how CTL model checking is done, and then we will see how CTL model checking actually helps in getting a streamlined implementation of LTL model checking. Right. So, underlying thing is a reachability checker, which is implemented by using some fixed point algorithms. We will study that, and then we will see that how CTL model checking and LTL model checking are built on top of that. So, given a LTL property var phi to be checked over a module M, we will do the following. So, what we will do is we will transform this phi into a checker automaton. Okay. Now, we will slowly understand what this means. This is a formal property written using LTL. So, you remember LTL with the operators always, eventual, until, etc. We will transform the property into a checker automaton. The automaton and the checker automaton will be not for var_phi, it will be for not of var_phi. Okay. So, it accepts runs which satisfies not var_phi. Okay. So, this is an automaton which will accept runs which are satisfying not of var_phi. In the last class we discussed what is meant by acceptance of a run by a automaton, right. Now, we extract a possibly non-deterministic finite state machine J from module M. Why can it be non-deterministic? Because the module M may have inputs and the next state inputs are non-deterministic. It is with the environment. So, you do not know what is the next state inputs, right. So, you can treat that as non-determinism, that the next state inputs are decided non-deterministically. Okay. So, that is why the state machine J that you extract out from M can be a non-deterministic state machine. Then we compute the product of the state machine J with this automaton B of not phi and check whether the product has any accepting run. Now, see, what would an accepting run in the product mean? It means that there is some run in J which happens to be an accepting run in B not var_phi, right. Now, if there is a if J has an accepting run for B not var_phi, that means that there is a trace in J which does not satisfy var_phi, because the accepting runs of B of not var_phi are the runs which satisfy not of var_phi, right. So, that run refutes var_phi. So, if we find any accepting run in the product, then we have found out a counter example trace. On the other hand, if the product does not have an accepting run, then we conclude that there is no counter example for var_phi in J. Alright. So, this is the philosophy of doing LTL model checking. Now, see, one thing is that the entire search, so these two are easy steps, I mean this is not a easy steps by any means, but these two are in terms of the algorithm. Okay, we just do some extraction, we will show how that is done. This is where the search is taking place, this is where you are traversing the state machine or the product automaton and looking for runs which are accepting, right. So, the search is here. Okay. Let us go through this whole thing using one example, then we will go into the detailed methods. So, here is a priority arbiter and the implementation is given here, this is the implementation, and we have the property which says either of the grant lines is always asserted. So, one of the grant lines should always be asserted, and in linear temporal logic we express that as G, G1 or G2. Now, first before we go into the actual model checking, just look at the circuit and tell me whether it is satisfied or not. Not satisfied. Why? Under which scenario? If both R1 and R2 are low, then in the next cycle both G1 and G2 will be low, right. So, we have seen that this is not going to hold. Now, let us see how does the model checker work in finding out that there is a counter example trace where R1, R2 are both low, and in that trace we will see that both G1 and G2 are low and therefore the property is violated. Okay. Now, let us see. So, first step is to extract the finite state machine out of this implementation. So, this is the transition relation that is derived out of this truth table. Okay. So, the truth table is present state, input, next state, okay, and these are the corresponding transition relations. So, G1 dash, which means the value of G1 in the next cycle, is the same as R1, right, and G2 dash, which is the value of G2 in the next cycle, is not of R1 and R2, okay, this one not of R1, R2 and not of G1, this one, this is not of G1, that is going to be the value of G2 in the next cycle, right. The start state is both requests are 0 and one of the grants is high, the other grant is one grant is low, the other grant is high. We could start with any start state, does not matter. Now, this is the transition relation. Now, see, the transition relation is here is a non-deterministic one, all right. So, let us understand this transition relation, because it does not look like a normal state machine. So, when I have an edge from one vertex here to the block here, it effectively means that it is edge to all of these, non-deterministic edges to all 4 of these, right. To make it more legible, I have done it like this, okay. So, you will see that this corresponds to the states, present state 0 0, this corresponds to the state 0 1, okay, this corresponds to 1 0 and this corresponds to 1 1. And now, we have 4 of these here, because these are the next state inputs, okay. Now, if your next state is 0 0, then your next state with the inputs can be 0 0 0 0, 0 0 0 1, 0 0 1 0 or 0 0 1 1, right, okay. So, for example, when you are in 0 0, okay, and you get input 0 1, okay, when you are in 0 0 and you get input 0 1, what are your possible next states? So, let us see, refer to this truth table. When you are in 0 0 and your input is 0 1, your next state is 0 1, okay, but what is the exact next state? The next state could be 0 1 0 0, 0 1 1 1, 0 1 1 0, because you do not know what are the next inputs. So, therefore, this edge actually is a collection of 4 edges, one going here, one going here, one going here and one going here. It is a collection of these 4 edges, right, which I have indicated by showing it only using one block arrow, okay. Now, so that is why I said that it is a non-deterministic state machine that comes out. So, what we had was, we had the present state input next state, and this state transition relation has present state input next state next input, and the moment you bring in the next input, you have this non-determinism. But this state machine now is a Kripke structure, because it does not have any inputs, every state has a well defined next state, right. So, it is a Kripke structure, and model checking algorithms will be defined over the Kripke structure, over closed state machines, clear. Now, so that is about creating the automaton for the finite state machine extracted out from the implementation. Now, we look at the property side. For the property, we first note that every LTL property can be converted to a Buchi alternating automata. I am going to talk about that later on in more formal terms. Right now, just note that the states of the automata represents the states of the property checker, and the automaton accepts all the valid runs, that is those that satisfy the property, okay. How does this help to check the property? So, let us see how it helps in checking the property. So, we will, for our example, this was our property. So, we will create the automaton for not verify as I explained earlier. So, what is not verify here? F of not G1 and not G2, right. So, if I put a not here, the G will become F and then we use De Morgan's. So, not G1 and not G2. Sometimes both grant lines will be inactive, that is what this says. Sometimes in the future both grant lines will be inactive. We will then search for a common run between this automaton and the FSM for the implementation, right. So, let us see how we create the checker automaton. So, let us consider a property FQ where Q is some Boolean formula. In fact, the property that we are looking at here is of that form. If you say that this is my Q, okay, then this is FQ, right. So, we can rewrite FQ as Q or XFQ, because FQ means either Q is true now or in the next state FQ holds. So, from the next state somewhere in the future Q holds. Okay. Now, let us understand one thing, that why are we breaking it down like this? The reason is that for any temporal property you can look upon it as something like this. You can say that a temporal property is one in which if I get some combination of values of the atomic propositions in this cycle, then the property will become true. For some combination of the atomic propositions it may become false, and for some of them there will be something that we have to check from the next cycle onwards. So, for example, when I look at FQ, there are two possibilities. I have Q in this cycle itself, okay. If I get Q in this cycle itself, then FQ is true. If I get not Q in this cycle, then Q is not true in this cycle, so I will have to wait for another cycle. So, in the next state I have to look for FQ. So, therefore, here it is XFQ, right. Let us look at P until Q, okay. What are the possibilities here? If I look at P until Q here, then the possibility is that if I get a Q, then I go to true, because it is immediately satisfied, okay. If I get not P, not Q, false, failure straight away. Otherwise, I have P, then not true. So, then what I have to do is I have to go to the next state and then check P until Q from there, right. So, every temporal property can be thought of as something to be checked here and something to be checked from the next cycle onwards. Every linear temporal logic property can be conceived in that manner, right. That means that given any property var phi, I can rewrite var phi into a form in which every term is either a proposition Boolean or it is a temporal property guarded with an X. So, P until Q will be written as P until Q is written as Q or P and X P until Q. Now, see what you have here is that this is Boolean, this is Boolean, and this is a X guarded temporal, right. Okay. So, in the automaton our states will be these, this. The state bits will correspond to the these propositions and the X guarded temporal properties. We are not going to go look inside the X. Whenever we find the X guarded thing, we know that this is nothing to be checked here. So, we will say that this is to be checked in future. So, let us treat that as a unit. Okay. So, my state space of the automaton is going to be determined by the set of propositions and the set of X guarded atomic subformulas, X guarded subformulas. Intuitively, that is what will be the state space of the automaton that we construct. So, let us go ahead and see for this example how we do that. So, therefore, we can have the following types of states: states that satisfy Q, states that do not satisfy Q but satisfy XFQ, and states that do not satisfy Q and do not satisfy XFQ. Right. Now, these two types of states are the states which satisfy FQ. States which satisfy Q satisfy FQ, states which do not satisfy Q but satisfy XFQ also satisfy FQ, and states that do not satisfy Q and do not satisfy XFQ, they do not satisfy FQ. Right. So, this is the automaton. Now, let us see. I have 4 states, states which satisfy Q XFQ, Q but not XFQ, not Q and XFQ, not Q and not XFQ. Now, this state satisfies FQ because Q is true there, this state satisfies FQ because Q is true here, this state satisfies FQ because though not Q is true here or Q is false here, but XFQ is there. So, this also satisfies FQ, right, and this state which does not satisfy Q and neither not XFQ, they are, it does not satisfy FQ. Now, see, this labeling of states with FQ is done even without looking at the transitions. In fact, when we construct this automaton, we will first decide the set of states. How? By unfolding the property and picking up the X guarded temporal terms and the propositions, and then if we have k of these types, then we will have 2 to the power k states in the automaton, and then we will say that that var phi is true in these states based on what are the things that are true here, right. So, we will substitute Q as 1, XFQ as 1 in that relation. Which relation? This relation. Here Q is true and XFQ is true. So, FQ is true. Here for this not Q and XFQ. So, we will satisfy, we will put not Q here. So, this is false, but XFQ is true. So, this is true. So, for each combination of these values of the subformulas and the propositions, we will see whether it satisfies var phi or not, okay, and we will label it accordingly. Then we will see how to put in the transitions. Transitions will now be inserted based on the following understanding, that we will have an edge from a state satisfying X of some property, provided that to another state, provided that this thing is true here. So, in our example, we are having this edge here because this has XFQ and we are putting an edge here because this has label FQ. So, we put this edge. Similarly, we put an edge from this to this. Why? Because this has XFQ and this is labeled by FQ. So, this is there. Similarly, XFQ and then this has label FQ. So, this edge. And similarly, this has XFQ and this is FQ, so this edge. Now, look at this one, this has XFQ, this has FQ, so we put this edge, but there is no edge from here to here. Why? Because this has not XFQ. So, we should not have an edge from here to a state which satisfies FQ. We should have edges from here to states which satisfy not of FQ. and which is the state which satisfies not of FQ? This one. So, that is why we have this edge, but we do not have edges from this one to any of these two, right. Now, let us look at this one. This one has x of not FQ. So, it has to go to have edges to those states which have not FQ. Here there is only one state which has not FQ. So, we have only this edge. Is it clear how we build this automaton? Yes or no? Yes. Clear? Right. Now, let us see one thing is that does this automata contain all possible runs by which FQ is satisfied? So, take any run in which FQ is satisfied. So, not Q, okay, then not Q, then Q, then not Q, and so on. Now, is this satisfied here? So, we start from this start state, okay, this state. Can I have the computer please? Can I have the computer please? So, it is here that we have this Q XFQ. Yes, finally we have the computer. Okay, from this Q XFQ, see we are here, right. So, if you get 1 not Q, okay, so where are we? We are here, right. So, this is a start state because we start with a not Q state, okay. So, we get a not Q, we remain in this, okay, again not Q, again not Q, and then when you get a Q, then you go to this one and you have that it is satisfying, okay. Now, you see that every run which satisfies FQ is there in this.
You told when we get a Q we go to the first one, but why not to that one?
It could be here also, it could be here or here, because we do not know whether Q will again happen in the future or not, we do not know that. So, you see that when we traverse this automaton, it could be either this or this, right. Now, if you want, so now remember that what are we trying to do finally? We will take the product of this with the implementation and try to find out whether there is at least one accepting run. If there is at least one accepting run, that is a counter example trace for var phi, because this automaton is for not of var phi, clear. Now, the problem with this is that there are some spurious runs here. Okay. Now, let us see what could be a spurious run. Suppose there is a run in which, okay, so we start here with a not Q, and suppose there is a run in which Q never actually happens. So, what is going to happen? You will keep going round and round in this one, right. So, that is something which is not an accepting run, right. So, what do we want? We want to say that states which satisfy Q must be visited infinitely often, only then it is an accepting run. We say it is an accepting run if states satisfying Q are visited infinitely often, okay. That is a Bukhi accepting condition. So, when we re-study our Bukhi automata, I had just mentioned what is a Bukhi automata in the last lecture, but what does Bukhi automata acceptance condition say? That the accepting set of states must be visited infinitely often. See, that is the requirement that we are getting here, that we have to visit this state satisfying Q infinitely often, okay. Then only we are guaranteed not to get stuck in this one, okay. And that can be expressed in terms of what are called fairness requirements. We shall see that later in due course of time. So, this is the summary of what we said just now, that every run satisfying FQ belongs to this automaton. Which are these runs? The runs starting from FQ level states. Okay. But all runs starting from FQ level states do not satisfy FQ. Example, runs that stay in state this state S forever do not satisfy FQ. Okay. Which runs satisfy FQ? Runs that start from FQ level states and visit states labeled by Q or by not of FQ infinitely often. Those are the runs which satisfy this. Okay. Okay. Did you get why we are having this or not of this? See, this is FQ, right. So, if you reach a state satisfying Q once, your FQ is satisfied, okay, right. But let us see what is happening here. When you were here in the beginning, you did not have Q, but you had promise that this state promises that in the that sometimes in the future Q will hold, right. That promise, this promise is met when you hit upon this state once. As soon as you hit this state, the promise is met because you have Q, but here you have made a new promise that again in the future FQ will hold. Now you have to meet this promise, okay. That promise is met when you again visit the Q level state, but then again you make another promise, right. When do your promises end? When you do not have any more Qs in the run, so then you must end up here. If you do not have any more Qs in the run, then this is where you must end up. Remember that we are talking about the acceptance of infinite runs, infinite sequences. So, then when you are here, then it requires not of XFQ. You have made a promise of not of XFQ, but you have Q here. So, somewhere in future you must have not Q, alright. That is met when you end up here. Then you keep on promising not Q and you keep on getting not Q, right. So, this is a loop in which you are visiting not FQ infinitely often. The other way that you could have ended up was staying in this loop forever, which is where you are visiting Q level state infinitely often. So, think of the thing that there are only two possible ways in which you can keep on generating infinite runs which satisfy FQ. Either you get stuck eventually in this one, or you get stuck eventually in this one, or it could be that you go around in this, that is also possible. That is another way of, because there also you are visiting Q level states infinitely often, right. Is that clear? So, that is what this is meant, that you have to visit states labeled by Q or by not FQ infinitely often. Okay. Now, the product. This is our state machine that we extracted out from the implementation. This is the automaton that we have created out of the property. And now we see whether there is a common run, and the common run is there, which is shown in red, in which you go from here and then stay in this loop forever. Okay. So, if you look at this run, in this run you have a path in which you are reaching FQ, and what is Q? Not of G1 and not of G2. Okay. See this product automaton, how do you construct the product automaton? What is the relationship between these and these? What is the relationship between these and these? No one is asking this question. What is Q? Q is not G1 and not G2. So what is that in terms of our state encoding? 0 0, right? So you are asking that whether you can reach 0 0. Okay. Where were you initially? You were in 0 1. Okay. So you were in 0 1, and what was the input? 0 0. Remember, R1 0, R2 0, and G1 was 0, G2 was 1. That was our initial state, right? This is where we were. This was our start state. Okay, and then from the start state we are showing a run in which not G1 and not G2 will happen. And what is that run? We go here. So 0 1 0 0 will take us to 0 0, and the next input can be whatever, but we have reached a state where both of them are 0. So this is the Q level states. These 4 are the Q level states. So we have reached a state which satisfies Q. So FQ is holding here, right? So therefore our original property which says that always G1 or G2 should be high does not hold. So it has found out the counter example trace. Okay. Is that okay? What are the state bits? The state bits here are G1, G2, okay, R1, R2. This is the 4 state bits. So this is G1 is 0, G2 is 1, R1 and R2 are 0, right? So this is a state machine. What is Q? Q is the Boolean formula not G1 and not G2. Which states have not G1 and not G2? These 4. So these 4 are the Q level states. This is our start state. We have to find out whether for FQ we have to find out whether there is a path from this state to this state, right? That is what the product of the two will give us. It gives us a path which satisfies FQ. So when you take the product of these two, okay, so this is our start state which is not Q because this is not labeled by Q, and then when you take this transition to a Q level state and then stay in this forever, that is a run which refutes which satisfies FQ and therefore refutes the original requirement which is G of not Q. What was G of not Q? G of not Q is globally G1 or G2. That was the property that we originally wanted to prove. Now we have found out a counter example for that because the negation of that property has an accepting run in the implementation. All right.
So if our start state is defined like 0 1 0 0, we start not starting from 0 1 0 0, we start from 0 1 0 1. Then like
if you start from 0 1 0 1, then what it is going to do is it will say that okay, from here 0 1 0 1 it will first take this, but what will it find out? It will find out that it will first take this, then this and then this. That is the path that is going to come out of this product. So in this, instead of this one first, it will first take this one once, then this, then this, right. So that path will be there in this, and so it is going to find out that path and say that we will find out a smarter way to compute this product later on, but first we will do some other model checking we will go into more formal ways of doing this, and then we will I will show you there is a smarter way of computing this product. Okay. So we will conclude this, and in the next lecture we will go into more details of it.